So we'll start with mean value theorems in today's class. The first theorem that we are going to discuss is the Rolle's theorem. So what this theorem states this here is, if a function y equal to f of x is continuous in closed interval AB. So if there is a function which is continuous in closed interval AB, that means in the graph of the function, there's no broken point in this interval. And differentiable in open interval AB. So differentiable means there are no broken points and no sharp edges in open interval AB. And f of A equal to f of B. So if these three conditions are satisfied, these are the given conditions of Rolle's theorem, then the conclusion is then this symbol means there exists at least, you just say there exists, C belongs to AB. C belongs to AB means it doesn't mean that C is only a unique value. You can have multiple values of C also in the interval such that the derivative at C is 0. That means the tangent at that point x equal to C will have a slope 0. So f dash of C represents slope of tangent at x equal to C. So that means the graph has a tangent parallel to x-axis. Geometrically, how do you interpret this? F dash of C is 0 means at the point x equal to C, if you draw a tangent, it is parallel to x-axis. So that is the geometrical meaning of this. So continuous means there are no broken points in the graph between A and B. And differentiable means there are no broken points, no sharp edges. And the y coordinates at A and B are equal. Then between A and B, there is a C such that f dash of C is 0. And this C need not be unique. There will be minimum one such value, but you can have multiple values like that, where the derivative is 0 means the tangent is parallel to x-axis. So we'll prove this graphically. So for a function to be continuous, the graph is not broken. So when you draw the graph of the function, the possibility could be, so if you draw this type of graph, the problem is it is continuous because the graph is not broken. No sharp edges or differentiable, but at A and B, if you look at the y coordinates, here f of A is not same as f of B. So this will not work out for Rolle's theorem given condition. So we have to draw it in such a way that it has to increase and then decrease so that f of A and f of B are equal. So suppose the graph goes up, comes down like this, such that at A and B, the y coordinates are same. So this point is A comma f of A and this point is B comma f of B. And clearly f of A is equal to f of B. This y coordinate is f of A, this y coordinate is f of B, they are equal. So you see that there are no broken points, so continuous in closed interval AB, no sharp edges, so differentiable. And clearly you can see, we can observe there is a point in between A and B. There exists a C in AB, so that if the coordinates of this are C comma f of C, the derivative at this point is f dash of C. And that should be 0 because the tangent is parallel to x-axis. So this is geometrically proved. F dash of C is 0 is geometrically proved. This is first case. But it is not necessary that you will have only one such point. You can even have multiple points like this. So let's say the graph is something like this. So again, this is f of A and this is f of B. So you can have multiple points like this between them. C1, C2, C3, where the derivative is 0. So here f dash of C1 is 0. And in the other case, you can see f dash of C2 is 0. And here f dash of C3 is 0. So there are multiple points where the derivative is 0. And you can also have a possible graph like this. Here also f of A and f of B are equal, it is continuous and differentiable. And there is a point where f dash of C is 0. And you can again have multiple points like this in this type of graph also. So f of A and f of B are still equal and the derivative is 0 at multiple points at C1, C2 and C3. So all this proves the Rolle's theorem. So then we have the theorem, Lagrange's mean value theorem. So here, this theorem states that if a function f of x is continuous in closed interval AB, so first two conditions are same as the Rolle's theorem only. So if a function is continuous in closed interval AB, then differentiable in open interval AB, differentiable in open interval AB. So here we don't have f of A equal to f of B. Then there exists C in open interval AB such that f dash of C is equal to f of B minus f of A divided by B minus A. And in case if you put f of A equal to f of B, f dash of C is 0, which will be the Rolle's theorem. So even Rolle's theorem can be derived from Lagrange's theorem. So when you draw the diagram, you draw it in such a way that it should just increase, again doesn't decrease. So it's something like this. So here f of A and f of B are different. F of A and f of B are different. This point is A comma f of A. This point is B comma f of B. And if you join them, you'll get a chord of the curve. AB is a chord of the curve. And the slope of the chord AB, if you see, it is f of B minus f of A by B minus A. So clearly we can see that we can have a point in between AB where the tangent is parallel to x-axis. So there is a point C comma f of C, and the slope of the tangent at this point is f dash of C. That f dash of C should be same as this. Because the chord and tangent are parallel, these two are equal. So this proves Lagrange's theorem. And it is not necessary that there should be only one such point. You can have multiple points also. So like, for example, if the graph is something like this. So you can see there are multiple points where the tangents are parallel to the chord. So this will hold for multiple points. So then we have one more theorem, Cauchy's mean value theorem. So this is same as the previous theorem. What we wrote for one function, we are going to write for two functions. So you can say if y equal to f of x and y equal to g of x are two functions which are continuous in closed interval AB. This is the first criteria. And second condition, differentiable in open interval AB and differentiable in open interval AB. Then the conclusion is there exists C belongs to open interval AB such that f dash of C by g dash of C equal to f of B minus f of A by g of B minus g of A. So since both are satisfying the conditions, you can apply the previous theorem separately for both the functions and then divide the answers to get this result. So this theorem you can apply and you'll get a result for f dash of C and g dash of C, divide them to get this result. So we don't need any proof again for this. This is Cauchy's mean value theorem. So here you can just say from the previous theorem, f dash of C will be f of B minus f of A by B minus A. And similarly, from the same previous theorem, g dash of C will be g of B minus g of A by B minus A. You just have to divide these two results to get this theorem, which is called Cauchy's mean value theorem.